Hello everyone, welcome to a new lecture in the series of data-driven model predictive control. In this lecture, we will be discussing subspace predictive control, which is a subspace-based data-driven linear MPC approach. Here is the overview of this lecture. We will be starting with the basic concepts and the algorithm for subspace predictive control or SPC, which is then followed by a numerical example. As the name indicates, subspace predictive control or SPC is a subspace-based data-driven MPC approach. SPC uses the input and output block angle matrices constructed from the training data to identify the parameters which will be used to define the model-based constraints. Unlike the previous lecture, here the identified parameters are not the ABC matrices. Instead, we can consider the parameters as some function of ABC matrices, which relates the predicted output sequence to the control sequence. Also, here we will not be using the impulse response data. Instead, an input-output data as in equation 1 will be used, which contains sufficient number of perturbations in the input that captures the transient behavior of the system. Some of the key terminologies used in SPC are listed here. The future horizon or prediction horizon, denoted by capital N, is the number of future samples of output predicted using the past data or current data. This notation capital N is also used in MPC as well to denote the prediction horizon. So here we follow the same notation. Then there is past horizon or measurement horizon denoted by capital M, which represents the number of lags of past data used for identifying the model. Another term is the training horizon or capital H, which is the number of training samples used for identifying the model. In SPC, the size of the Hankel matrices will depend on these three parameters, as we are going to see in the upcoming slides. Now, using the training data, the input and output block Hankel matrices can be constructed as in equation number 2. Here UP and UF are the input block Hankel matrices, which represent the past and future sequence. And UP can be defined as the block Hankel matrix H with capital N row entries, capital H column entries, and the vector U0 as the first element. Capital U0 denotes the first column of this matrix, and capital U1 as the second column, and so on. Here, each column of UP and UF represents an input sequence or can be considered as a data window. And the next column is the sequence shifted by one time instant or can be considered as a shifted data window. This indicates these block Hankel matrices contains a moving window of data which captures the dynamic behavior. Here we use the past or measurement horizon and the future horizon to be the same, or in other words, capital M equal to capital N. That is why both UP and UF contains capital N number of row entries. If we were using different past and future horizons, then UP will contains capital M number of row entries and UF will contains capital N number of row entries. However, in our derivation, all the four block Hankel matrices will contains capital N number of row entries, which will basically simplify the notations. Similarly, this YP denotes the past output data and YF denotes the future output data. And each column of these matrices can be denoted by a column vector as shown here. These four block Hankel matrices are the key components in a subspace-based system identification. And therefore, in subspace predictive control as well, these four matrices will play the central role. We use a relationship between these four matrices to define the model-based equality constraint in MPC. And next, we will derive that the future output Hankel matrix YF can be represented as a linear combination of UP, UF, and YP. In the initial lecture, we derived the prediction equation where this capital Y1 can be written as capital AY X0 plus capital BY capital U0. And similarly, capital Y2 can be written as capital AY X1 plus capital BY capital U1 and so on. Using this, the elements of YP and YF can be computed as in equation 3 and 4. where we obtain y1 is equal to ay x0 plus by u0, y2 equal to ay x1 plus by u1, and so on. Now, by defining the capital XP, which contains all these initial states, and capital XF, which contains all these initial states, we can compactly represent equation 3 and 4 as in equation 6, which results in yp equal to ay xp plus by up, and similarly yf is equal to ay xf plus by uf. Now we can define the matrix capital Cu as in equation 7, which can be considered as a reversed controllability matrix and will be used in the next equation. We have the elements of capital XF can be computed using the equation for predicted state as in equation 8, which can be compactly written as a raised to n x0 plus Cu capital U0. Similarly, other predicted states can be computed until xn plus h minus 1, which will be equal to a raised to n xh minus 1 Cu capital UH minus 1. Here, all these terms xn to xn plus h minus 1 were stored in a matrix capital XF as defined in the previous slide, and all these terms x0 till xh minus 1 were stored in the matrix capital XP. This gives the relation between these matrices as xf equal to a raised to n xp plus Cu up. And these two equations were obtained in the last slide. In this equation for yf, we can substitute for xf from this equation, and it can be further simplified, which will be coming up next. Now we will be using a result from the literature which says that for any observable system and with capital N satisfying this criteria, there exists a matrix M which satisfies equation 10. This indicates that a raised to n can be written as minus may, which will be used in the next equation, where we substitute xf in the equation for yf and substitute this criteria from this equation. Simplifying the terms, we obtain yf equal to p1 up plus p2 yp plus by uf, where p1 and p2 are defined as in equation 12. And this equation we obtained in the previous slide is the central equation in SPC, which basically says that the future output data yf can be represented as a linear combination of the past input data up, past output data yp, and future output data uf. Now defining the parameter matrix P, which contains this matrices P1, P2, and By as its elements, and the data matrix S, which contains the matrices UP, YP, and UF as its elements. And we can rewrite this equation as YF equal to PS, which is a linear equation and can be solved for the parameter matrix P as in equation 16, where we multiply this equation in the right hand side by S inverse, which gives P equal to YF into S inverse, where we use the pseudo inverse of the matrix S here. Once the parameter matrix P is computed from the training data, we can take its elements P1, P2, and By to define the model-based constraint as in this equation. In SPC, we use the Hankel matrix equation derived in the previous slide to compute the predicted output sequence. Here, the predicted output sequence is denoted by capital Yk plus 1 and the control sequence Uk, which can be considered as the future sequence in the MPC. And these YP1 and UP1 are considered as the past data sequence which are used in SPC. Here, the predicted output sequence is only one column of the output Hankel matrix. Therefore, we will be using the Hankel matrices with only one column, which are denoted by YF1 and UF1. And similarly, the past Hankel matrices are denoted by YP1 and UP1. Yk plus 1 or YF1 is the Hankel matrix with capital N row entries, only one column, and Yk plus 1 given k as the first element. We can define the control input sequence capital UK, which is UF1, that is Hankel matrix containing capital N row entries and one column entry, and start with UK given k. Similarly, we can define the past data matrices yp1 and up1. And if we substitute all this in the Hankel matrix equation, we can obtain yf1 or yk plus 1 will be equal to p1 up1 plus p2 yp1 plus dy uk. Then in SPC, we will be using this equation to define model-based equality constraint. And this leads to the optimization problem for SPC as in equation number 19. So here, this term is same as the predicted output sequence or capital YK plus 1. And this capital QY and capital RU are the block diagonal matrices containing the output and control weighting matrices along its diagonal as discussed in lecture 2. In practice, we know the output reference value using which this matrix capital YR can be computed. And since we don't have a state space model, defining the steady state condition using the state space model and solving it for the control reference UR will be difficult. So therefore, we haven't included the control reference in this control term. If we know the control reference, that term can also be included here. In SPC, this optimization problem is solved at each time instant to find the optimal control sequence UK star. Then the first element of the sequence is applied to the system. Algorithm 1 summarizes the steps for implementing SPC, in which firstly we use the historical data or the training data, which is consisted of YD and UD, to construct the block Hankel matrices, which are UP, YP, UF, and YF, where the size of these matrices is defined by these parameters capital N, capital M, and capital H. You can normally select the past horizon or this capital M same as the future horizon N. And even if we are using different values for N and M, the same algorithm can be used. But the only difference is that the size of these P1, P2 matrices will be different. Using these block Hankel matrices, we can compute the parameter matrix capital P, which consists of this P1, P2, and By. Then using the elements of P or these matrices P1, P2, and By, we can define the optimization problem for MPC as in equation 19, and which can be solved for finding the optimal control input UK star. Then in SPC, we apply the first element of this optimal control sequence at the current instant, and then solve this optimization problem for each time instant until the end of the time horizon. Next, we move on to a numerical illustration of SPC. Here, we consider a fourth order system with one input and one output, for which the parameters are chosen as in equation 20. The training data is generated by simulation of an LTI system with these parameters, and the input data will be containing sufficient number of perturbations. The simulation parameters for SPC are chosen as in equation 21, in which we select capital N is equal to 30, and in the simulation, the capital M or the past horizon is chosen as different to the prediction horizon. And even if we are using a different value of M, the same equation which we derived in the SPC can be used here as well. And the value of capital H is chosen as 400, and the weighting matrices for the MPC are chosen as here. Figure 1 shows the response of the linear system with SPC, where we can see that the input contains sufficient number of perturbations to capture the transient dynamics. The subplot B shows the output response with SPC, and the plot C shows the control input. Note that here during the SPC implementation, the first 20 instances of the output are chosen from the training output, where 20 is the value of the past horizon used in the SPC. And the MPC problem is solved from time instant 21 onwards. That's why the output for the initial few instances in this figure B does not matches with the reference value. The MATLAB codes for the numerical implementation of SPC can be downloaded from the link given in the description. That leads us to the end of this lecture. Thanks for watching.